底记得吗？我记得是。Okay, last time, guys, we were getting at the page 12. Page 12, since we have done the minimum variance controller, which is I think that will be the most straightforward version of the minimum variance controller. So from look at this, actually it cancel out all the system dynamic. Finally, only leave like hold on. Like this. Finally, we achieved the mean. If we substitute the equation number 4, so this is minimum variance controller, and stuck equation number 4 into 3, and it gives it's going to cancel out all the system dynamic, the process offset. It cancel out all the past error, the current error, and the process gain and process offset, and leave the future error alone. So which is valid for all the time period. So finally, the minimum variance is attained. So I think to implement the controller, typically we're going to use a different, the more practical format. So please refer to the book, the textbook on page. Let me see, where is that? The page 182, the example 5.2. Okay. Then we plug. We can rewrite the equation number 4 into this form. So this is AYT minus CYT, like this. Yeah. Like this. So this is our minimum variance controller. This is in equation number 4. Since finally we arrive the YT plus 1 equal to the epsilon T plus 1. This is the absolute cancellation. Then we arrive that. So the epsilon T plus 1 going to be equal to the YT plus 1. For the implementation purpose, so which can be rewritten into this form. So the controller is equal to the A minus C divided by B and YT. YT is the observation. This is the control output, directly control output, for sure. Then how about ACB? Yeah, let me see what is A and C and B, ACB. So how can we get that? Let me see that example, A and B and C. So question, how could we get the estimate of A and C and B? How could we? John?
So that
Yes, how can we get that? So into this form, let me show you. Yeah, like this. Like this. How can we? So last time we arrived the mean member in this no dynamic. Then we move to the example number 2 on page 182. This, like this equation number 3, y plus 1 equal to plus the ayt be equal to the bxt plus the c epsilon t plus the epsilon t plus 1. So yeah, then, so how can we get a, c, and b? The a, so for a, so it is an autoregressive model. So we can get that for sure, since based upon the ARIMA. How about B? B, so we need to estimate through the transfer function. C, for C, how can we get that, John? What kind of model? What kind of model is it? C.
MA.
Yeah, good. The C, the moving average. That's cool. Hold on. Yeah, let me change into the style. The moving average. That's why this is not a difficult problem. So we can directly solve it for sure. And well, let's see. Okay. Then plug in number 6 into the number 3. It is the original equation into that. So you can see that A, B, C, and xt equal to the A minus C over B, yt. So finally, yt plus 1 plus the cyt equal to the epsilon t plus 1 plus c epsilon t, or well, so we just move around, move all the things to the left hand side into this form. So finally, see the page, see the textbook, page 183. The first equation. Okay. So solving the first order difference equation with the initial condition into that, the y minus epsilon t plus 1, and factor out c yt minus epsilon t. So this is like so see the middle of the page 183. The page 183. Okay, then solving the first order difference equation with the initial condition, then the yt equal to the epsilon t plus a kct raised to power t, as long as the c is less than 0. C, we mentioned previously, this is a parameter in the moving average. So as long as the absolute value is less than 1, so it is an invertibility condition. And with the initial y0 minus epsilon 0 equal to k. So like this. This is initial condition in here. This is initial condition. So you can see that when t approach infinity, since c is value less than 1, so when t approaching infinity and second term vanishes, so yt going to approaching epsilon t, right? So the yt is approaching. Epsilon t. So yt approaching epsilon t, which attain the minimum variance, right? So it is quite obviously. Then we like to see how can we formulate is a control block diagram. So see the page 184. Yeah, let me change the other phone since it is not a good. No, okay, hold up. I want to. Yeah, let me see how can I. Yeah, hold on. Yeah, let me do how can I change. Page 185, hold on. Like this. Okay, then let me see. Okay. Can you see the screen? Can you?
Yes.
Okay, then we'd like to see the text on page 185. Or, well, so this case then, hold on. What is that? Okay, like this. So epsilon t come into the 1 plus c backwash operator, 1 plus a backwash operator into that, like this. We just represent in this form. Yeah, let me. Equation number 3. Like this. Okay. We just formulate into that. So that produce the disturbance, and xt times the b backwash operator divided by 1 plus a backwash operator is right here. Yeah, let me see that. Okay, you just reformulate into this equation, then you will find xt into that. So this is the signal. This is the disturbance and the producer y for sure. Then yt, once you get the yt, okay, let me see that. You get the yt, hold on. You get the yt, then how can we get the control? And the a minus c divided by b and multiplies yt to produce xt. So once you get yt and multiply a minus c divided by b, and you get xt. And xt and multiply back. In here, you get a xt. And you multiply the 1 plus a and divide by b, and then and b and 1 over a, and into that produce a signal and the disturbance once again. So this is the control block diagram. So called hold on. So that is called the control block. Called the control bar diagram. So let me see the illustration. See the page 184. See, this is transient response provided by using the minimum mean square error control of the example 5.2 by using that. So this is epsilon t. Epsilon t going to the epsilon t is a minimum variance control. This is the level of the minimum variance control. Okay, let me type it. The epsilon t. So you can see that epsilon t represents the level of minimum variance. And see what's happened. This is our control output. Pei Zhen, would you like to comment? What's happening? What happened? And once does the YT converge to the minimum variance control level? Pei Zhen? Hello? Does it converge? Does it converge?
Yes.
Yes.
Yeah, absolutely. When the time time goes by, so you can see the output. See that? So in this period, we'll call the transient. Yeah, let me see that. In this period, we'll call it is called the transient period. Transient. The up and down fluctuate a little bit, called the transient period. Transient period. Then finally, it is approaching the minimum variance control. You can see that when the time is after the t is greater, is exceeding 27 or 28 or even 30. Yeah, it's almost achieved the minimum variance control. Okay. Okay, then we going back to the slide. Okay, then so how can we construct our like this? Just rearrange this equation. Move the YT can be represented B over 1 plus A backwash operator XT minus 1. And also the 1 plus C, 1 plus A, 1 plus C going to be the MA. So 1 plus A going to be the AR. So this multiply the epsilon into that. Okay, yeah. So epsilon T into the 1 plus over C over 1 plus A. Epsilon T into that to produce a signal. And then, so once we have a YT is a multiply A minus C over B, produce XT in here. However, remember this is the deadbeat controller XT minus 1, deadbeat controller. Hold up, which is a deadbeat control. Only the time lag is 1, right? Deadbeat controller. So So this is a b over 1 plus a backwash operator. There's a backwash operator right here. Let me see that. So b over 1 plus a backwash operator. This is a backwash operator right here. xt times backwash operator. Where does it come from? Right here. Right here. b backwash operator divided by 1 plus a backwash operator. Exactly. So the idea, the whole rationale come from the control block diagram and this equation. Okay. So you can just transform, put that into xt, and the b backwash operator divided by 1 plus a backwash operator. Okay. Okay, then we'd like to consider the optimal prediction. Let me the forecasting on page 186. Yeah, let me see that. Yeah, finally right here. Okay, then remember this is admissible control. On page 185, we call it is admissible control rule. As long as xt is admissible, if it is of the form, so that means the control mechanism can be developed. So let me just type it. It is admissible as long as the control mechanism and I. Hold on, array. You can see that it is admissible as long as the control mechanism can be developed based on xt, yt, a Riemann transfer function. Then it is called, it is termed, or it is coined admissible rule. So optimal control rule number 4 was obtained, making the one step ahead forecast equal to 0. So this is a great idea. Idea is on the page 186, right here. Yeah. Right here. Yeah, please use your highlighter, or in pad, just highlight this. The optimal control law, equation 5.3, was obtained by making the one step ahead forecast equal to 0, which is target. Yeah, to make yt on target. So the forecast error is equal to 0. Equal to 0, or only subject to the future error. So I would like to say that only subject to future error. Then it is done. MMSE forecast. I know, quite straightforward, and it is pretty similar to the equation we derived in the chapter 4. So like this is a yt plus 1. This is a true observation. This is the observation minus prediction. This is a one step ahead forecast based upon the t and the progress one step ahead prediction error epsilon t plus 1. So if the forecast equal to the minus ayt plus bxt plus the c epsilon t, then if those equal to 0, So the yt plus 1 equal to the epsilon t plus 1. So this is going to be equal to that. So we can predict that. So if the deviation from target is equal to 0, so you can consider this. If the deviation from target is equal to 0, then, I'm sorry. So by contrast, in the uncontrolled case, xt equal to 0. So what does it mean, uncontrolled case, x equal to 0? How could we? If xt equal to 0, what going to happen? Let me see that, like this. If this is equal to 0, see that? No control. No control, that means no control, that is the open loop, like a SPC. That means the SPC is like a process monitoring scheme. We just leave it alone, and we only construct the process limit or control limit for monitoring as long as the signal is found or any process anomaly occurs. Then the signal is given. Then we just trace back what is the sign of causes that could be, and correct the sign of cause and bring the process back to control. So it is an open loop. So see the prediction like this, only this equal to the minus yt plus the c epsilon t. This is question number 7. So compare number 7 to number 4. Okay, let me see. That's number 7. Let me see. Where is the number 4? Number 4. Okay. Number 7, number 4. Okay, this is number 4. See the difference? This is our minimum variance control, XD, remember. Number 7 is this. Don't you look so familiar? We can see that. So we see that minimum variance control is selected such that it cancels out the one step ahead forecast. So this is the something we would like to cancel out. A and C. Let me see that. A and C. See that? So we select this in order. How the XT is selected? XT is selected in the way in order to cancel out what? One step ahead forecast. That's it. Let me see. The XT is selected in order to cancel out the one. That's it. So this is what I'm trying to say. And this is cancel out with the one step ahead prediction or forecast. Therefore, there's a need for good. Then there's a need for good forecast. So we need to produce that. That's why we need the minimum variance control. So optimal forecast will supply controller with the most up-to-date process information. Then optimality criteria MMSE is to consider 3 with the xt equal to 0. Okay. So then look at the page. Yeah, let me see that. Okay, let me see. Yt plus 1. Okay, c plus 1. Okay, then look at the page 187 right here. Okay, we start right here. We start page 187. So you can see that yt plus 1 based upon this. Yeah, let me see that. We set up, excuse me, when we set up xt equal to 0, x2 equal to 0. Okay, see that? See that? 1 plus a backward operator times yt equal to the 1 plus c backward operator times the epsilon t. As long as there's no control, so we would like to consider what is the best for our optimal forecast, minimum variance forecast. So in which case, we temporarily to consider no control. This is to enforce xt equal to 0. Okay, then. Then like this, okay, we understand that this epsilon t, and then in the numerator, we do it intentionally. In order to cancel out this, so this is 1 plus a, we plus a, we add extra term and must be it need to be canceled out. So plus a backward operator minus a backward operator, and the reparameterize. So 1 plus a divided by 1 plus a is 1 for sure, and then the second term plus reparameterize c minus a. We factor out backward operator c minus a times the backward operator divided by 1 plus a backward operator epsilon t. So we factor out epsilon t plus 1 as well. So finally, what do you say? Equation number A. So fantastic. You can see that yt plus 1 right here on the left hand side equal to the epsilon t plus 1 plus c minus a backward. Okay, we just a backward operator multiply the epsilon t plus 1. This is epsilon t divided by 1 plus a backward operator. So when you see the equation A, so it can be decomposed into two terms. Let me see. Yt is decomposed into two terms. Okay. What is the first term? Easy and quite simple. It's a random error, future error. Can we do anything about that? No. We need to only leave it alone. You can see that we can only best the performance by leaving it alone, and then try to work out the second term. Right? How can we work on the second term? As long as to let the pass error, this is pass error, and also including the present error. As long as the observations are available, then yeah, it can be. Yeah, it can be. So as long as we can cancel out this to let the yt equal to this equal to 0, then we are done. Things from equation number 3, xt equal to 0. Yeah, epsilon t can be represented as this. Let me see equation number 3 like this. Yeah, that's for sure. That's for sure. And plug in this equation into number A right here. Yes. The epsilon t, the c right here. Epsilon t c minus a over 1 plus a backward operator epsilon t epsilon t equal to that. Let me see that. How can we get the epsilon t? Let me find the equation epsilon t. Okay, this xt equal to 0, epsilon t equal to the 1 over a, 1 plus a divided by 1 plus c times yt. 1 plus a, 1 plus c, yt. 1 plus a backwards operator over 1 plus c backwards operator yt, and plug in here. Is epsilon t is right here, epsilon t. The c minus a, 1 plus a backwards operator coming from right here. Then we had this one. So finally, you can see that cancel out. Boom, cancel out. Boom. Then epsilon t plus 1, future arrow, is c minus a for sure, and then 1 plus c, backwards operator. No, backwards operator yt. So into that. Then going further. So let me see that. So from here into that, we obtain that at the current time t, we have expressed the next observation right here on the left hand side as a function only of the current and the past observation and a future error. Let the y hat denote the function of the yt, the current observation, past observation, yt minus 1, minus 2, that forecast future deviation from target for sure. So we would like to do that since this is our yt, this is our future observation, and we wish to find the y hat such that this is yt plus 1 minus y hat, the plug in here, like this. Okay, back to our, so we have it. So this is our yt for sure. Then, so we like to find the minimum variance control or the forecast function. So we want to find what is the y hat such that the expected value standing on time t and the yt plus 1 minus y hat squared, take the expected value, is minimized. So for sure, yt plus 1 and the minus y hat in here. Y hat, let me see that. Okay, then yt is equal to this. Where does this come from? This is yt. This is yt. Okay, no control right here. For the time being, no control is involved. No control is involved. Okay, then into that. Then this is like, let me say, okay, this is a plus the b squared equal to the a squared plus the 2ab plus the b squared. Okay. Then take the expected values. We just multiply the expectation operator into each term. So this is the E epsilon t plus 1 sigma. So we understand this is sigma epsilon square for sure. Expected value of this one, since the expected value at this future arrow, this is cancel out. Then this is constant, A is constant, C is constant. So finally write this. So how can we minimize this? As long as we let our forecast equal to c minus a plus 1 plus c backwash operator times yt, then second term cancel out. Then the whole thing the minimum variance is attained, right? So finally, we get the expected value. The mean square error must be greater than or equal to the future error, sigma epsilon square, with equality when the second term cancel out. So how can we make the second term cancel out? Straightforward, with equality when the one step ahead forecast equal to this. So the optimal minimum mean square error one step ahead forecast is equal to that. Yt plus 1 given t and put the carry on the top. C minus A divided by 1 plus C backwash operator Yt. Okay. So it's the expected value of the Yt plus 1 for sure. Or yeah, I would like to put in the control formula. I'm sorry, formula. Put into a control formula. So we multiply this into left-hand side. So this is Yt plus 1 given t times C. C y hat t, the backward shot t given t minus 1 equal to the right-hand side C minus A times Yt. So this is this. Then we have, so this is once while we get the previous one step ahead, move this one. So what is the next one step ahead? Equal to the C minus A. We obtain those parameters from model building, multiply current observation, and minus the last observation times C. So then one step ahead forecast error. So this is Yt observation subtract minus minus our forecast right here. So we put the tail on the top. This is the error. Error is we calculate the difference between the observation and forecast. So see that. Let me see that minus. Okay, Yt plus 1 is right here. Okay, Yt plus 1 is right here. Yt plus 1 is this one. Epsilon t plus 1 c over a 1 plus c Yt. Yep, this one minus one step ahead forecast. C minus A, 1 over C backwards Yt. And then you can see that exactly cancel out. Leave the future error alone. Yeah, what a beautiful formulation, right? So it is so clever. As long as we let the forecast at the minimum and the optimal minimum variance control. So you go cancel out the current and past error. Only leave the prediction error alone, right? Then like this. Finally, we have this one. Yeah, see that? So what we obtain if the rules in section 3.5 in the previous chapter until the very end of chapter 3 were used instead. The the one step ahead focus error is, or innovation is like this, like this. So where we use the difference notation to distinguish forecast error from the residual. So yeah, this is not residual, so use a forecast error. Residual is ET, so this is a forecast error. So forecast error are called innovations. Innovations right here, because if they were 0, it would mean there's nothing new to learn from the past data at time t. So any non-zero forecast error can be sort of giving us new information. That's why we call the innovation. Call the new information. Yeah, let me see. Yeah, it's equivalent to innovation. There's something new coming around. I'm sorry. New information right here. So any non-zero forecast error can be sort of given us new information about our forecasting model in relation to the underlying process. Okay, then we move to the two-step ahead forecast. Yeah, let me see that. Okay, two-step ahead forecast. What is a two-step ahead forecast? Two-step ahead focus, like we are at today. For example, we would like to project 2 days later. Like I would like to see the day after tomorrow. So like to see 2 days later, then this is the two-step ahead forecast. And then, based upon the same formula, we still in XD equal to 0, still in force, no intervention involved. So in here, intervention. Okay, I'm sorry, intervention. Okay, remember, as long as they read the textbook, it mentions, as long as it mentions intervention, that means by human, or manipulation by human, that is, we're talking about the control mechanism. So at time t, so we like to standing on the time t plus 2, since we like to standing on, hold on, we're standing on the time t, we like to progress 2 days later. So we like to yt equal to that, yt equal to epsilon t. We need to trace back yt. Finally, you're going to see this equation like this, all right? Back to here, right here. No intervention yt plus 2 equal to the 1 plus c backwash operator over 1 plus a backwash operator epsilon t plus 2. Okay, based upon the same equation, difference equation, like this. Okay. now we have this, right? Then like before, multiply into that. Epsilon t plus 2 plus the c epsilon t plus 1, since there's a backwash operator right here. Then, okay, I'm sorry. In order to cancel out, we have a 1 plus a backwash operator in the in the denominator. So we intentionally to plus a epsilon. This is a 1 plus a, so we need to cancel out 1 plus a as well. So we intentionally add one term, a plus epsilon t plus 1, and which need to be canceled out. So we subtract that. So then it turns out to be this. Cancel out, cancel out. This is epsilon t plus 2. And reparameterize the c minus a epsilon t plus factor out t plus 1 over 1 plus a backwash operator, right? The same trick as before. Okay, we have a break. Okay. Okay, everybody, we back to the class. We back to the class. Let me. So, hold on. Okay, then it can be represented as the arrow and the future arrow. So then this is 2 step ahead focus. So from which we get, we just multiply 1 plus a backwards operator to the left hand side. So in here, this is epsilon t 1, and this is epsilon t a epsilon t plus 1, and move to the left hand side. 1 c minus a epsilon t, so epsilon t plus 2, c minus a epsilon t plus 1. From equation 8, yt, let me see that, yt epsilon t c minus a, yeah, let me see that. How can we? Epsilon t plus, yes, we can do that. And the minus a epsilon t. Hold on, how can we get that? Yeah, let me see that. Yeah, how can we get this? From here, yt plus 2. Yeah, let me see the textbook. That will going to be more straightforward. So yeah, like this, we take a look at the textbook. Equation 5.8 is right here, based upon this one. This is a future arrow plus the current and previous arrow based upon this. So we just put that into the t plus 2 based upon the equation number 5.8 into 5.9. So in analogy, in analogy to the question 5.8, we have a question 5.9. Adding and subtract the c, a backwards operator, c minus a epsilon t. No, this a is extra. This is no a. I'm sorry. No, there's only c minus a backwards operator. So we have this. This equal to that, the epsilon t plus 2 c minus a 1 plus a backwards operator based upon this, like this, okay? So we have it like, let me see, hold on. I have a equation 5.7, like this, this form. Then we can just reparameterize into based upon the equation 5.8, we have an equation 5.9. So let me see that. So we intentionally add this, c minus a epsilon t plus 1. So we're going to subtract c minus a epsilon t plus 1. right? Epsilon t, yes. And the subtract that we just combine into this form, So since epsilon t equal to the 1 plus a over 1 plus cy, y in here. Epsilon t, let me see. Epsilon t. Let me see that. Epsilon t. Yeah, let me epsilon t. Epsilon t. Yeah, right here, in here. Or directly, we can see that. No, I would like to give the form. No, not here. Yeah, this is kind of messy. Yeah, like this. So epsilon t can be represented as yt times 1 plus a over 1 plus c. Okay, 1 plus c. So 1 plus a over 1 plus c. So we have this future arrow. This is current arrow. Then epsilon t, so this is epsilon t plus 2 plus c minus a epsilon t plus 1. So we like to factor out into the future arrow and the current arrow. This is the objective we like to achieve. So we like to factor out the future arrow and the current arrow and the past arrow. That's it. This is our objective. Then we have epsilon t plus 2 right here, for sure. We have epsilon t plus 1. So this 2 term belong to the future arrow. And okay, then since epsilon t is 1 plus a over 1 plus c, 1 plus a over 1 plus a cancel out. So that turns out to be a minus c over 1 plus c yt. Okay, so this is the current observation. And this is the c constant, this a and c are constant, the current observation. So yeah, this is kind of beauty. The current observation is a constant for sure. So we have it. So we shows yt plus 2 as a function of the current observation and the past observation. So why? Since there's a backwash operator, this is the current observation and the past observation, we are done. The past observation, what about past observation? It's a constant as well. It's a constant as well. So this is known in advance. The future arrow. When we would like to derive the mean square arrow, minimum mean square arrow forecast, we just leave the future arrow be alone. These two, be alone. So so and the two future arrow, looking at the process time t. So them like here. Like here. Okay. Then, so which can be decomposed in the future arrow t plus 2 period ahead, the 1 period ahead. So this is the current observation and the past observation. Yeah. Then we like to get y hat. So what is minimum mean square arrow forecast? To minimize this as before, we plug in yt plus 2 yt plus 2 equal to that. This is the equation number 10 minus y hat. So once again, like yt, yeah, let me see that. This, okay, this. So first two things, the first two things consider as one. The last two terms are considered the second one, like a plus b squared, a squared, plus 2ab plus a b squared is b squared. The a squared is epsilon t plus 2s squared plus the c minus a epsilon t plus 1 squared. 2ab equal to 0. And the 2ab, this time this is also cancel out since this is a future arrow. So just do the same as we done before. So yeah. So what is the best strategy for minimize the expected value of the mean square error? To let the forecast equal to this: a times a minus c divided by 1 plus c backwash operator, and divide n times yt, and let this two term be alone. Why? Since this is a future error. Okay, so the mean square error must be greater than this plus this, right? These two are this is totally unavoidable. So this, as long as we can do about a certain to let the y hat equal to this, and the last one can be canceled out. So with equality, when the y hat equal to 1 times a minus c divided by 1 plus c backwash operator. Therefore, the two-step ahead forecast or two-step ahead prediction that minimize the variances, or no, this is a mean square error. MSE. MSE is equal to multiply this into left-hand side. Yeah, let this, this. Yeah, let me t plus to this. Let this equal to that. So yt plus 2 given t, and this is 1 plus c, and move the second term to the right-hand side, minus c yt plus 1, given t minus 1, since this is a two-step ahead. So the time lag between them are 2. So then this is a minus c yt. So this is our so show the yt plus to a function of that. So we wish to get the forecast, so cancel out that term. So we have equality when we let y equal to this one, that is yt plus 2 given t hat. So again, the last expression is what we would obtain if the rules for computing forecasts described in the section 3.5 were applied to. So two-step ahead minimum mean square forecast can be given by this one. So from 5.10 from here. 5.10. This is the two-step of forecast error. So we know this should be tail. The yt plus 2 given t should be tail equal to the yt plus 2. Yt plus 2 is this one. Okay, let me just shrink it a little bit. Yt plus 2. yt plus 2 minus yt plus 2 given t hat. So cancel out AC like this one. So is this one. Yeah, let me see that. So forecast error. See that. Let me see that. ACYT. ACYT. The go around the cancel out. The lead, only the first two terms are left, like this. So yt plus 2 is 1, yt plus 2. 1, 2, 3. 1, 2, 3. Question number 9. Yeah, AC minus AC 1 plus A over YT. Now we just reparameterize this one. This is YT. Okay, then yeah, let me see that. And subtract YT plus 2 given T is this one. This one, subtract this one. Subtract this one. So this is going to be canceled out. The left is we factor out epsilon t plus 1, epsilon t plus 2. This is 1 plus the C minus A backward operator. So it's going to be the moving average. So 2 step ahead forecast. Subject to a series of, I'm sorry, moving average. I'm sorry. First order moving AVE. The 2 step ahead is subject to a series of the moving average. So you might want to think why this is true. Let me see that. From 10, this 1, 2, 3, 10. Equation number 10. Let me show you where is the 10. 10 is right here. Epsilon t plus 2 C minus A, AC, this YT, and cancel out the last one. Leave this 2 alone. Okay, so they're going to cancel out and leave the feature error alone. So this is quite similar as before. Okay, then we stepping a little bit further, like consider the general case step ahead forecast. So general case step ahead forecast consider a more general ARIMA form. Now, actually, they are integrated, as I mentioned before. As I mentioned before, before we start to fit the armor auto to the data, what should we check first? 正好, would you like to comment something? As I mentioned before we can start to feed the model to the data, what should we check first? 上好 ，Hello。
没声音啊。
What do you say?
Check ACF and PACF.
Yeah, that's like a sample ACF, right?
Yes.
Like sample. Thank you. For what? Why do we need to do that?
为什么要这样做？
Auto
correlation.
Now, first I would like to check the stationarity, right? It is stationarity. If it is not station, so what should we do?
Yes.
So we need to
different.
Okay, difference.
Yes.
The data. Okay, Yu, after difference the data, what should we do next, Yu?
SACF?
Yes, we check. That's great. Thank you. We check the sample autocorrelation function of the data in for stationarity. Jun, we check the sample autocorrelation function of the difference data for stationarity. Then how would you know the difference data is stationary or not? Jun. Junzong.
Yeah.
How would you know?
We can check using the portal test.
And so what kind of test you like to use?
What it's called? Luden box.
Oh, okay. No, this is later. This is quite in the really late part. So we need to stationarity. So if, so you can see that we're going to check. We're going to check the partial. I'm sorry. We're going to check station. Hold on. We're going to check the sample autocorrelation function, right? So to see it is exponentially
Case.
right?
Yeah.
It is exponentially decrease or is behave like way of sine. Remember, like a sine function, up and down, also decreasing. So going to up and down. So this is alternating and decreasing as well. So yeah, this is how we make the process to be stable. Then we can fit the armor, right? Okay. So back to the case step ahead forecast. So consider a more general ARIMA model like this. we assume there's a no component is considered. So A times YT equal to the C times epsilon T. Epsilon T, following a Y sequence, we assume A polynomial and the C polynomial are of order n. Yeah, this is a pre-assumption. We would like to find the k step ahead predictor. So this is a y hat, the t plus k given t. And then such that we like to minimize the mean square error, MMSE, minimum mean square error of the yt plus k given t hat. So that is equal to the observation minus the pre-forecast. Take the square, since t plus k is a random variable, take the expectation. So this is a random variable as well, so it can be minimized since this is a form of the random variable. So at time t, we want to predict yt plus k. We like to predict this. So we have yt plus k c over a epsilon t. Yt plus k here, the c over a times epsilon t. T plus k. This is equation 11. So remember the variables epsilon t minus 1, epsilon t minus 2, and so on and so forth can be estimated from the data. Why? Hey then, why this is true? Hey then.
Right.
So what does it mean? The variables epsilon t minus 1, epsilon t minus 2 can be estimated from the data. What does it mean? Why?
I mean,
Why? How come? Since it is already happened, the data, the observation, which is available. So like a YT is the current observation. So yeah, then the epsilon t, the forecast error. Yeah, let me type it. Epsilon t is yt minus yt hat. The yt is a constant. Yt hat is forecast, so both are constant. Both are constant. That's why this not random variable. Not random variable. That's why. Okay. Then how about this? Epsilon t plus 1, epsilon t plus 2. Yeah, this is a future error, not happening yet. So Jun Zhong, would you like to say for those future arrow, can you do anything about that? Can you?
No.
No, okay, just leave them alone, right? Okay.
Yeah.
Cool, thank you. So then we separate, okay, move to here. Right here, okay. We're going to separate into this ugly form, equation 5.12, okay. This is really ugly. So we separate those two groups of terms by writing 11 into that. C over A, yeah, blah, 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 and then C over epsilon t plus k, right-hand side of the equation 11 can be separated into two groups terms by rewriting equation 11 as the future arrow use F indicate future. This F polynomial. I'm sorry. Is referred to as the future. And the future can be represented 1 plus F1. This is the coefficient F2. So F is F1, F2, F3. This is the coefficient in the polynomial of the F. That was your operator. Just don't, please don't scare off. This is only our coefficients. Then for this is the K. This is the K that's we factor out the system time lag, and G over A epsilon t plus K. So since this cancel out, so once while the backwards operator K cancel out the K right here, the epsilon t. So this is current arrow and the past arrow. The second term, the G. So use the G known G1 and G2 until Gn minus 1, Gn minus 1. So yeah, this is the current. This is past. The yesterday. This is day before yesterday, the 2 days before yesterday, 3 days before yesterday, blah, blah, blah. And then, so this is G polynomial. So G polynomial is referred to the past. Already happened. The past, that means this is the current plus the past. Right? So then we have this form. This is called Diophantine. Okay. Then equation 11, using where is it? 11 right here, can be written as based on the equation 11 and 12. Then where's 11? This yt plus 2 and epsilon, this can be decomposed into this and this. Okay. Then the yt plus 2, yt plus k can be represented into this form. F epsilon t plus k plus the g, yeah, excuse me, yeah. Yeah, let me see the textbook. This is straightforward. Okay, then remember the order, like we mentioned here. I'm sorry. Yeah, the order of k minus 1, the order of n minus 1, right here. Remember, we introduced two new polynomials, f polynomial of order k minus 1, for sure. As long as the K is K step ahead forecast. N is the polynomial of the A polynomial for sure. So then 5.11, this one can be written this one. So this is F T plus K, and hold on, epsilon T plus K into this is A over C Y T K. Let me see that. Hold on, this is F. Excuse me. 5.11. 5.11 YT plus K. This is C. Okay, equal to this plus this. G over A. Okay, can be written G over A, and this is Bagorshi operator K multiply epsilon T plus K is epsilon T. Okay. So before we proceed any further, we pause here for example of how this partition of error is made. Okay, let me take an example of this one. Okay. Yeah, let me example 5.3. Okay. Example 5.2. We take this. Okay. 1 minute. Please read this example through. Read everything through. So 1 minute. We stop here for a while. Please use a one minute or 2 minute read this through. So I'll be back in 2 minutes. Okay, then let me, for example, I'm back. For example, so we have this one over there. Yeah, I would like to put example. What is example? Come on. So, no. So we have this one. Okay, example 1, consider. Okay, go to 2. Okay, let me directly look at this. So partition of errors needed in forecasting. consider the process in example 5.2 as before. We have from equation 5.9. Equation 5.9. Yeah. So this is future arrow. This is current on the past. Okay, 2-step ahead forecast. So in this case, notation just introduced. We have a K since a 2-step ahead forecast. So K equal to 2 for sure. The polynomial of A, is right here. It's n equal to 1. Since right here, polynomial of A. So the F is right here. F is the order of this is the F is a future polynomial related to the future observation. So K equal to 2, this is 2 minus 1. So this is 1 plus F1 backwash operator, only this 2 times. And N is equal to 1. N equal to 1, this is 1, this is 0, this is only the genome, 0. It's like, okay, let me see that, like this. So in this case, so K equal to 1, so F1 is a C minus A. Backwash operator, C minus A. So the F is a 1 plus the C minus A. This is epsilon T plus 2, epsilon T plus 1. So this is 1 plus the C minus A backwash operator. So F1 is a C minus A. 1. The epsilon T plus K. F1 backwash operator, F2 backwash operator, Fk minus 1 backwash operator of the K equal to 2, the minus 1. So F1 is equal to C minus A. Okay. Then for the G in here, since N equal to 1, so we only have the initial condition, genome. So genome is, in this case, so genome is AA minus C. So since, let me see that. G polynomial in here, this is epsilon C. So this is the G polynomial, genome, G1, G2, and so on and so forth. So, so once why we can just fit it into this form. So this multiply into that, this is epsilon T, this is A polynomial, and then we just represent G into that. So in which case, G is A times the parenthesis A minus C. So this is genome. So, okay, is any question so far? This is just a tryout. This is an initial tryout. The initial tryout to let us understand how can we get the F, the G. Yeah, that's it. Since they're going to be called Diophantine equation. So going to mention this later. So yeah. So we've done that. Okay. Okay, then second. So the second term in 13 can be obtained. 13, what is the 13? Okay, can be obtained. So when K equal to, this is F1 G1. So this equation, YT, this is F plus the G over A epsilon T. So this is the equation. the G over A epsilon T. G epsilon T can be represented. Let me see that can be obtained from epsilon T. Yeah, epsilon T can be represented as A over C times Y. A over C times Y. So plug in into the 12. Into the 12 right here. So finally, we have FGA. So this is into this epsilon T is AC. ACY. Okay, ACY. ACY. This is GCY. Finally turn out GCY. So just reparameterize GCY. So just turn into the Y, and let the Y hat be any forecast function in order to minimize the mean square error, like before. The YT plus K is this one. The F plus the G over C Y. Since we like to just since we have this, we don't want to epsilon T. We just transform into the YT. Just transform into YT into that. We obtain this one. This put into the minimum mean square error into that. So that is to say A minus B squared, like before. YT plus K. YT plus K is this two. F plus the G over C YT minus Y hat squared. So this two. This is A squared and plus the B squared. This A squared plus the B squared plus 2AB. Or 2AB, you can see that F. What is F? What is F related to? The F polynomial. What is F? F is right here. F is the future arrow, right? Do you see that? Do you see that? F?
Yes.
So the F. So when take the expectation of the future arrow got to be equal to 0. It won't matter of the seconds of the something just following, right? So then this is the present and past arrow, so it won't matter. Then so the A squared plus the B squared. So when we take this one, the future arrow, there's nothing to do about that. The only best way you can do is to let the last term equal to 0. So minimum mean square error equal to the expected value of the future error plus the bias square. So in order to make the second term, so in order to minimize this one, the best way is to let the second term cancel out. So Y hat equal to the G over C times YT, like here. So yeah, the G over C YT is then this is greater than. So once this cancel out, the mean square error is equal to the mean square error of the future error. So this must be greater than or equal to the future error. And future error, and what is the future error? Straightforward, quite straightforward. This is 1 plus F1, F2 until Fk, K minus 1, epsilon T. And finally, just a reparameter 1 plus f1 squared, f2 squared, fk minus 1 squared, sigma epsilon squared. Okay, then we have a break.
那你说要不要把荧幕先关掉？
OK， 这样可以了吗？
可以关掉了。
OK，Thank you。 糟糕啊！各位同学，我们讨论一下。我看今天是看一下，讨论一下这个行程要怎么安排。你听得见吗？
听得见。
OK，今天是6月2号，所以说还有9号、16号跟23号。23号我们就是 Turn Project 就第2个好了。这次 Turn Project 因为线上的关系，我就出了简单一点。那一样用，本来想说让大家去做比较复杂的 Turn Project， 那我想说就做这个 Minimum Variance Controller 的 Project， 本来还要加 Self Tuning。So on June 23rd, we're going to have the final project presentation. So let me see. This is June 23rd. On June 23rd, so we are going to have the final project presentation. So yeah, I hope, yeah, I'm not quite sure it is online or not. Not quite sure of if it is online or not. So we are not sure. So we hope, yeah, the COVID alert level 3 can be lessened a little bit down to the alert 2. Then we can go back to the classroom. So it depends the CDC final decision. So if the alert has been down to level 2, then we go back to classroom for presentation. If still maintained at the level 3, the COVID alert still maintained at level 3, then it must be done virtually. Yeah, that is everybody okay? Then need to share. So then how can you? So okay, you're going to share your screen by running the program. By the share screen on your computer. Is everybody okay with that?
Yes.
Okay, Goy is okay for you?
Yes.
Okay, thank you. John?
Yes.
Okay, Yu?
Yes.
Okay, Sanghao?
Yes.
Okay, then so it also need to be individual project. Going to individual project, you also use whatever you use C#, C# or you use Python. This are all acceptable. Then otherwise anything, and then we can also use well, if you like to use a VBA, that's okay. Then so this I'm going to on the project of okay, yeah, no, not generalized, the minimum variance controller. Okay, I will address. So I hope I can wrap up the minimum variance controller by next week. Okay, so let's go with this schedule. Okay, then. Yeah, let me hold on. Let me turn this off a little bit. hold on, let me turn this off. Okay, then. So we have this one. Then so the optimal k-step ahead forecast is given by the number 14. It's number 14. So with equality whole, when the y hat equal to the k-step ahead forecast equal to g over c times yt, g over c times yt is expected value of the yt plus k, the random variable is expected value of random variable, which is minimum mean square error forecast, MMSE. So the k-step ahead forecast is given by this one, the prediction error observation. This is observation minus predict. Observation yt. Yeah, let me see that. Okay, then observation. Let me see that. Where's the yt? I'd like to see the yt. Okay, it's a yt. The y minus forecast is the second term. G over c times yt. So second term cancel out. So the forecast arrow leave the f to be alone, like this one. To be alone, right? The f is going to be the series of the polynomial. Is this one? Is this one? Is this one? Series of polynomial. So yeah, I think this is quite obvious and apparently evident. So following a moving average of the what is older, k minus 1. Yeah, quite straightforward. So then, to find the coefficient G and F, G and F is this, when we factorize this, y equal to f, g over a epsilon t. Would like to find the f and g. Is it like a Diophantine equation? Like a Diophantine equation in the contour theory. Let me show you. Here. Then this is difference equation, future arrow. So we also put the control right here, the transfer function added back, the future arrow, current arrow. So now the Rmax, hold on, general solution. Okay, no. We like to see the Diophantine. What is the dial? Okay, right here, right here. Okay, equation 5.15. So as can be seen from the above equation, the key to obtaining the MMSE forecast is to find the G and F polynomial separately. These two obtained by equating coefficient of the power like power of the in the Bagauche operator in the Diophantine identity. C over this one, B times over A times Bagauche operator G, the Diophantine. So which going to be addressed like that? We use the Diophantine, C, F, and G. Yuck. Okay, let me see that. Let me find an equation. Let me see that. Okay, this. C over A, F, G over A. So this times A, both sides, we multiply A polynomial, C equal to the AF and the backwash operator of the time lag G, C over AF and GA. And the C, FA, backwash operator G. It's called the diaphanting. Yeah, is that clear? Yeah, just refer from here. From here, multiply A on both sides. So we can move on in 12, then based upon this. So now we move to the contour theory, general solution to minimum mean square error control problem called the RMAX problem in here. Okay, general solution to the minimum variance or MMSE, minimum mean square error or minimum variance control problem. So which is considered a generic transfer function in here. We just introduce a transfer function into that to see that. So we call the RMAX in the this is the RMAX model in the field of econometrics. Yeah, let me type in Mandarin. We call it econometrics. So in terms of the mathematics to perform the economy analytics. Economy analytics. Okay, then why we call the max R max? So it is referred to exogenous variable. Exogenous variable is x. Xt is to the monetary strategy or something related to the macro or microeconomics economics. Okay, reform something like that. Control the exchange rate. So control some strategy on the market. And excuse me, I just turned it off. I'm sorry, I turned off the. Okay, then solution to the general minimum variance controller. So we add this. So as time t, we need to decide on yt in the following equation in the RMAX. So ay equal to the bxt minus k. K is a system, or the k is a system lag. In which case? Yeah, system lag. And say epsilon t plus k is in the RMAX form. Epsilon t coming C over A. Epsilon t coming C over A produce disturbance. Then B over A, xt coming B over A produce the signal or process gain. Process disturbance. And this summation produces a y and fed back to the controller. So the question, how can we set up the controller in order to provide the recipe xt? Okay. So in here, so K is the system delay. So second term on the right hand side contain this, the arrow unknown. This is a future arrow, and the past and current arrow can be estimated from the residual. Thus, we can rewrite the expression like this: B over A xt, C over A. C over A is like this. Where is C over A? C over A. Okay. C over A is this. C over A equal to the F plus the backward system time delay, G over A epsilon T. Can be represented, just a plug in here, plug this into that equation. Yeah, into that equation. Okay, done. So this is equation 16. We can write the 15 or 13 or into that. So where F is the order of K minus 1, K is a system delay. G is the order N minus 1 and the order of the AR, where the N is the maximum of the NA, is this one. And B polynomial is a transfer function right here about the exogenous variable xt. I'm sorry, I should write MB, I'm sorry. MB, I'm sorry. MB is referred to the order of the exogenous variable MB. Then NC is a order of the polynomial C. C is right here. It's C. C. This is NA, MB, and NC. Okay. So the whole thing, this equation 16, can be represented as AY times BX, multiply A on both sides, times AF, and plus the G epsilon T, G epsilon T, this equation. Okay. So the coefficient of G, F, and G are obtained by equating coefficient of power like or like power formula in terms of backwash operator. So like here. So this can be represented that, and the C equal to that is Diophantine. C, let me see, show you C. See this is based upon the C equal to the F A system delay G. Okay, so power like so C is known, right? And A is known, and K is known. So the F and G can be obtained by matching both sides. By MAT matching all terms. I'm sorry, by using the back. Okay, by matching all the terms of both sides by using the backwash operator of match on both sides. So I'm sorry. Then from the definition of the RMAX system, then yeah, let me see that. Yes, okay, over A. Okay, that's fine, we get. So we just reparameterize, rearrange. So this in terms of the RMAX, RMAX is right here. This is RMAX, this is RMAX. The A, Y, B, X, C, epsilon. A, Y, B, X, C, epsilon. So epsilon T, just move this A, Y minus BX divided by C. Divided by C is epsilon T. So we have an equation 18 right here. Okay. Plug in 18 into 16. 18, this one we have epsilon T into the 16. We have epsilon T into the 16. Epsilon T. This right here. Okay. 18 into the 16. So B over A 16. Where is the 16? B over A F GA times epsilon T. And yeah, this is kind of messy, I understand. So yeah, let me just read again. B A F GA and epsilon T. Yeah. A F G A epsilon T. So we have this. So you can try yourself at home. Then yeah, this kind of let me see. F over C. So into 18 to that xt. So we reparameterize xt and xt here. We factor out xt. This is a b over a minus bgac, and factor out. And we also have a system delay. And this is yt, that plus gc yt right here. And this is f. Okay. In terms of 17, what is 17? Let's see, this is diophanting. Okay, we have a diophanting. So GC, diophanting. C equal to the AF and backwash average G, C equal to that. Into GC, we just plug in here into that. So we have AC. So just represent in the polynomial form. The F epsilon T plus K G over C YT, no problem. And the B, we have a common denominator AC. So this is a factor of C minus factor of B, and the C minus G, and G polynomial, and the backwash operator system delay. Okay. Then further, the GC stay put, and AC BC. Let me see that XT BC BG. C is equal to C minus G backwash operator C minus G backcross operator. C move this term to the left hand side. C minus G backcross operator equal to FA. So we have FA right here, and the AA cancel out. Finally turn out to the BF over C. Yeah, I understand this is kind of messy. Yeah. Then further. So let the xt be some function of the current observation and past observation. Then we want to find what is exogenous, the level of exogenous variable, such that, yeah, expected value of the yt plus k squared. Since we assume it is a deviation from target, so this is deviation from target with directly square. So this is f g over c b f over cxt square. We assume y is a deviation from target. Excuse me. Y t is to be the deviation from target. The target, typically target, is referred to the specification. Then, so try to minimize that. So then we have a plus, okay, that second, since the future arrow, this is the current arrow and past arrow, current and past arrow, or current observation, past observation, a plus b squared, a squared plus the b squared plus the 2ab. The expected future arrows cancel out. The turnout, yeah, to be minimized as easy as can be. The best we can do is leave the first term to be alone. The best is let this equal to 0. So then the xt can be obtained. Let the last term to be 0 and xt. This is the level. The level of xt can be computed, right? So this, let me see that the cancel out, and this is 0. Then the variance going to be due to the moving average of the order k-1. So it's greater than expected at f, 1 plus f1 squared, f to the fk minus 1 squared, sigma epsilon squared. So which arises from uncontrollable error with equality. Wow, we have it the last time. G over c yt plus a b over f over c xt equal to 0. This is equal to 0. Then multiply both sides on c. So what is xt? Move this term to the right hand side. Then xt equal to the minus g right here, minus g over bf times yt. Then we are done. From the above, we obtain the minimum variance controller. The minimum variance control law. This is minus g over bf times y. Then done. So they're going to be the first version of the minimum variance controller. You can start work on that. So they're going to be the first part of the final project. This equation. Okay, let me. Finally, we have this. Using. Okay. This. The first part, minimum variance or minimum mean square error control law. Going to the first part. The first part. mean square arrow controller is this part. You might want to work on that. Maybe now, okay. So today I need to stop here since in the afternoon, 1 o'clock, I'm going to have oral defense for my EMBA student. They're going to be the all afternoon. I need to do some preparation. So I lead a class let go a little bit earlier. So I think the content is quite messy. It's kind of complicated, and I hope you are strongly suggested to read several times of the textbook and my slides. Then you might want to start your project very soon. Any question? I need to stop here since I have an oral presentation at the 1 o'clock. Any question? 有没有问题啊？
No.
没有。
Then we are going to have a final term project 3 weeks later. So yeah, you might want to work on that. Okay, I will distribute the term project. We're going to have a specification what you're going to turn. You must hand in. I will send it to the line group to let you know. Okay, so working hard. So I see you next week. So please read the book. Read the book. Okay, see you. 佩珍录完影就那个上完 YouTube 把链接寄过来给我。
好。
Okay, see you next week. Bye. So you can log out, well, whatever you feel comfortable.